Tonight, we're going to explore something that will fundamentally change how you see your place in the cosmos. We're going to discover just how small Earth really is. And I'm not talking about comparing it to the Sun or Jupiter. I'm talking about the true scale, the scale that makes Earth almost disappear. Because here's the thing most people don't realize. Earth isn't just small. It's so incredibly tiny that finding the right words to describe it becomes almost impossible. By the end of this journey, you're going to see our planet and yourself in a completely different light. Before we dive in, if you enjoy these explorations of space and our cosmic perspective, a quick like or subscribe would really help this channel grow. It's a small gesture, but it makes a real difference. Now, let's begin our journey. Let's start with Earth itself, our home. The planet we walk on every day. From our perspective down here on the surface, Earth seems enormous. You could spend your entire life traveling and still not see every corner of it. The continents stretch for thousands of miles. The oceans cover about 71% of the surface. Mount Everest rises nearly 30,000 feet into the sky. To early humans, Earth was everything. It was the entire universe. The sky above was just a dome with lights on it. The ground beneath was flat and went on forever in all directions. This made sense based on what they could see. When you look out at the horizon, the Earth does look flat. The curve is too subtle to notice without getting very high up. Earth has a diameter of about 7,926 miles at the equator. If you wanted to walk around the equator and somehow could walk on water, you'd cover about 25,000 miles. At a steady pace of 3 miles per hour, walking 8 hours a day, that would take you about 3 years and a month. That's a long walk. Earth is genuinely large from a human perspective. The surface area of Earth is about 197 million square miles. To frame this magnitude, if you wanted to visit every square mile and spent just 1 second in each location, it would take you over 6 years of continuous travel. The United States, one of the largest countries, covers only about 3.8 million square miles. That's less than 2% of Earth's total surface. But here's where things start to shift. When you zoom out just a little bit, when you start comparing Earth to other objects in space, it begins to shrink. Not physically, of course, but in significance. Earth stops being everything and becomes just one thing among many. And as we keep zooming out, it gets smaller and smaller until it becomes something almost impossible to see. Our first stop on this journey takes us to our nearest neighbor. The Moon orbits Earth at an average distance of about 238,855 miles. That's roughly the distance you'd travel if you drove around Earth's equator 9.5 times. It seems far, and it is far by human standards. When Apollo astronauts traveled to the Moon, it took them about 3 days to get there. The Moon itself has a diameter of about 2,159 miles. That's roughly 27% of Earth's diameter. So the Moon is smaller than Earth, but not dramatically so. If Earth were a basketball, the Moon would be about the size of a tennis ball. But here's what's interesting. The distance between Earth and the Moon is about 30 times Earth's diameter. Imagine placing 30 Earths in a line between us and the Moon. That's how much empty space exists in that gap. Most people don't realize this. When you see pictures of the Earth and Moon together, they're usually shown much closer than they actually are. The reality is that there's a vast amount of nothing between us and our closest neighbor. This is our first hint that space is mostly empty. Even in our immediate cosmic neighborhood, the distances are enormous compared to the sizes of the objects themselves. The Moon's relationship with Earth is actually quite unique in the solar system. Most moons are tiny compared to their parent planets, but our Moon is relatively large. In fact, the Earth and Moon system is sometimes called a double planet because the Moon is so substantial relative to Earth. The Moon's size has real effects on Earth. It creates the tides we experience every day. The Moon also helps stabilize Earth's axial tilt. Without it, Earth's axis might wobble dramatically over time, causing extreme climate variations that could make complex life difficult or impossible. Looking at the Moon from Earth, it appears about the same size in the sky as the Sunday. This is a complete coincidence. The Sun is about 400 times larger than the Moon, but it's also about 400 times farther away. This coincidence gives us total solar eclipses where the Moon perfectly covers the Sunday. The Moon is also slowly drifting away from Earth. Each year, it moves about 1.5 inches farther away. This happens because of tidal interactions. Billions of years ago, the Moon was much closer, and a day on Earth was much shorter, perhaps only 5 hours long. For now, the Moon remains our closest companion in space. And in 1969, humans walked on its surface for the first time, a moment that showed what we're capable of when we push the boundaries of exploration. Now let's examine the Sunday. The Sun is the reason we exist. Without its light and heat, Earth would be a frozen rock hurtling through space. But the Sun is also where Earth's dimensions truly begin to pale in comparison. The Sun has a diameter of about 864,000 miles. That's 109 times larger than Earth's diameter. The Sun's volume is so immense that approximately 1.3 million Earth-sized worlds could occupy the same space. Consider that for a moment. Every mountain, every ocean, every city, every person who has ever lived, all of human history happened on a planet whose volume represents less than 1/1,000,000th of the Sun's interior. The Sun contains 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, and comets combined, makes up only 0.14%. The Sun is also about 93 million miles away from Earth. We call this distance 1 astronomical unit, or AU. Light from the Sun takes about 8 minutes and 20 seconds to reach us. If the Sun suddenly disappeared, we wouldn't know for over 8 minutes because the light telling us it's gone would still be traveling toward us. To grasp this distance, consider that a vehicle maintaining highway speeds would require 176 years to traverse this 93 million mile gulf. The fastest spacecraft humans have built, the Parker Solar Probe, takes months to reach the Sun, even though it's traveling at speeds exceeding 400,000 miles per hour at its closest approach. The Sun is actually a pretty ordinary star. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It's about 4.6 billion years old, roughly middle-aged. It has enough fuel to keep burning for another 5 billion years or so before it begins to die. The Sun's power is staggering. Every second, it converts about 600 million tons of hydrogen into helium through nuclear fusion. This process releases an enormous amount of energy. The Sun produces more energy in 1 second than all of human civilization has produced in its entire history. The surface of the Sun has a temperature of about 10,000 degrees Fahrenheit. The core, where fusion occurs, reaches about 27 million degrees Fahrenheit. The pressure at the core is about 260 billion times Earth's atmospheric pressure. The Sun also produces solar flares and coronal mass ejections. These are enormous releases of energy and matter from the Sun's atmosphere. When directed at Earth, they can cause beautiful auroras near the poles. But they can also disrupt satellites, power grids, and communications. Looking at the Sun reminds us that Earth is not the center of the solar system. For most of human history, people believed Earth was at the center of everything. It took brilliant thinkers like Nicolaus, Copernicus, and Galileo Galilei to show that the Sun was at the center and Earth orbited it. This was humanity's first major lesson in cosmic humility. Our solar system extends far beyond Earth and the Sunday. Let's zoom out and see where Earth fits in this larger structure. The inner solar system is home to the rocky planets. Mercury hugs closest to the Sun, baked and frozen in its extreme orbit. Venus follows, shrouded in its toxic atmosphere. Then Earth, our blue marble, at the perfect distance for liquid water. Mars rounds out the inner worlds, a cold desert that once knew flowing rivers. These 4 terrestrial planets cluster relatively close to our star, all within about 1.5 times Earth's distance from the Sunday. Between Mars and Jupiter lies a vast gap, populated by the asteroid belt. This region contains thousands upon thousands of rocky fragments, the building blocks that never quite became a planet. The largest, Ceres, spans only about 580 miles. More than 13 Ceres could line up side by side across Earth's diameter. Despite containing millions of objects, the asteroid belt is mostly empty space. If you flew through it, you'd likely never see an asteroid with the naked eye. The distances between them dwarf their tiny sizes. Then we reach the realm of giants. Jupiter dominates the outer solar system like a king surveying its domain. With a diameter of about 86,881 miles, it's about 11 times wider than Earth. Jupiter's volume is so immense that 1,321 Earths would barely fill it. This planet is massive, beyond easy comprehension. It contains more mass than all the other planets combined. If Jupiter were a hollow sphere, you could fit every other planet in the solar system inside it, with room to spare. And yet, Jupiter itself is tiny compared to the Sunday. About 1,000 Jupiters could fit within the Sun's volume. Saturn follows Jupiter in the outer solar system, nearly as impressive in scale. With a diameter of about 72,367 miles, Saturn could swallow 764 Earth-sized worlds within its bulk. But Saturn's most distinctive feature isn't its size. It's the magnificent ring system that encircles it. Made of countless particles of ice and rock, these rings extend tens of thousands of miles from the planet's surface, yet they're remarkably thin. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a piece of paper. The ice giants, Uranus and Neptune, dwell in the cold darkness beyond Saturn's orbit. Both are smaller than Jupiter and Saturn, but still dwarf Earth. The volume of Uranus equals roughly 63 planets the size of ours, while Neptune's interior could accommodate 57 Earth-mass bodies. These distant worlds take decades or centuries to complete a single orbit around the Sunday. Neptune, the most distant planet, requires 165 Earth years just to make one trip around our star. Beyond the planets lies the Kuiper Belt, stretching from Neptune's orbit outward for billions of miles. This region is filled with icy bodies left over from the solar system's formation. Pluto, once considered our 9th planet, resides here among thousands of similar frozen worlds. Pluto is only about 1,473 miles across. About 5.4 Plutos could line up across Earth's diameter. The Kuiper Belt represents a vast reservoir of primordial ice, a frozen archive of materials from the solar system's birth. But even the Kuiper Belt isn't the true edge of our solar system. Far beyond, almost incomprehensibly distant, lies the Oort cloud. This vast spherical shell of icy objects surrounds our solar system like a cosmic bubble. It begins at about 2,000 times Earth's distance from the Sun and extends outward to nearly 2 light-years. That's almost halfway to the nearest star. Objects in the Oort cloud are so far away that they're barely affected by the Sun's gravity. They're more like prisoners loosely held than objects firmly in orbit. No human eye has ever seen an Oort cloud object directly. We know it exists only because comets occasionally fall inward from this distant realm, their icy surfaces vaporizing as they approach the Sun's warmth. The point is this: our solar system is vast. It extends for trillions of miles, and in all that space, Earth is one small rocky planet orbiting at a distance that's relatively close to the Sunday. In a proportional model where the Sun equals a basketball's diameter, Earth would measure no larger than a peppercorn positioned 26 feet distant. You'd need a football field to show the orbit of Neptune at this scale. Let me give you more detail about each of these worlds to really drive home how Earth fits into our planetary neighborhood. Mercury is a small, dense world covered in craters. It has almost no atmosphere, which means there's nothing to protect it from meteorite impacts or to trap heat. Mercury's surface endures temperature swings exceeding 1,000 degrees, from 800 Fahrenheit under direct sunlight to minus 290 in darkness. Earth's atmosphere protects us from such extremes. Our temperature variations are tiny by comparison. Mercury takes 88 Earth days to orbit the Sun, but it rotates very slowly. One day on Mercury, from sunrise to sunrise, lasts 176 Earth days. This means that one Mercury day is actually longer than one Mercury year. Imagine living on a world where a single day lasts longer than a year. Time would have a completely different meaning. Venus is sometimes called Earth's twin because of its similar size, but the similarities end there. Venus has a thick atmosphere made mostly of carbon dioxide with clouds of sulfuric acid. The atmosphere is so thick that the surface pressure is about 90 times higher than Earth's. That's equivalent to the pressure you'd experience if you were 3,000 feet underwater in Earth's oceans. The greenhouse effect on Venus is extreme. Venus maintains a relentless 900 degrees Fahrenheit across its entire surface, trapped by carbon dioxide's greenhouse effect, hot enough to liquefy lead. Venus is actually hotter than Mercury, even though it's farther from the Sunday. This shows what can happen when a greenhouse effect runs out of control. It's a cautionary tale for Earth. Venus also rotates backward compared to most planets. While Earth and most other planets rotate counterclockwise when viewed from above the North Pole, Venus rotates clockwise. No one knows why. It might have been knocked over by a massive impact billions of years ago. Venus also rotates very slowly. One day on Venus lasts 243 Earth days. Combined with its orbit around the Sun, this means the Sun rises in the west on Venus and sets in the east. Mars is smaller than Earth, but in many ways more similar to Earth than Venus is. Mars has polar ice caps made of water ice and frozen carbon dioxide. It has seasons, though they're about twice as long as Earth's because Mars takes about 687 Earth days to orbit the Sunday. Mars once had liquid water on its surface. Ancient riverbeds and lake beds are visible in images from Mars orbiters and rovers. But something happened to Mars. It lost most of its atmosphere. Without a thick atmosphere, liquid water can't exist on the surface. It either freezes or evaporates. Today, Mars averages a frigid minus 80 degrees Fahrenheit, though equatorial summers occasionally reach above freezing, while polar winters plunge far deeper. The atmosphere is so thin that the surface pressure is less than 1% of Earth's. Why did Mars lose its atmosphere? The planet is smaller than Earth, so its gravity is weaker. But the main reason is that Mars lost its magnetic field. Earth's magnetic field is generated by the motion of molten iron in our planet's core. This field acts like a shield, deflecting the solar wind. A stream of charged particles from the Sunday Mars once had a magnetic field, but its core cooled and solidified, shutting down the field. Without this protection, the solar wind slowly stripped away Mars's atmosphere over hundreds of millions of years. Mars has two small moons, Phobos and Deimos. Phobos is only about 14 miles across. It orbits so close to Mars that it goes around the planet 3 times each Martian day. Phobos is also slowly spiraling inward. In about 50 million years, it will either crash into Mars or break apart from tidal forces, forming a ring around the planet. The asteroid belt sits between Mars and Jupiter. It contains millions of rocky objects, but the total mass of all asteroids combined is less than 4% of the Moon's mass. If you were somehow flying through the asteroid belt, you wouldn't see asteroids everywhere like in movies. The distances between them are enormous. You'd have to aim carefully to hit one. But something happened to Mars. It lost most of its atmosphere. Without a thick atmosphere, liquid water can't exist on the surface. It either freezes or evaporates. Today, Mars averages a frigid -80 degrees Fahrenheit. Though equatorial summers occasionally reach above freezing, while polar winters plunge far deeper. The atmosphere is so thin that the surface pressure is less than 1% of Earth's. Why did Mars lose its atmosphere? The planet is smaller than Earth, so its gravity is weaker. But the main reason is that Mars lost its magnetic field. Earth's magnetic field is generated by the motion of molten iron in our planet's core. This field acts like a shield, deflecting the solar wind. A stream of charged particles from the Sunday Mars once had a magnetic field, but its core cooled and solidified, shutting down the field. Without this protection, the solar wind slowly stripped away Mars's atmosphere over hundreds of millions of years. Mars has two small moons, Phobos and Deimos. Phobos is only about 14 miles across. It orbits so close to Mars that it goes around the planet 3 times each Martian day. Phobos is also slowly spiraling inward. In about 50 million years, it will either crash into Mars or break apart from tidal forces, forming a ring around the planet. The asteroid belt sits between Mars and Jupiter. It contains millions of rocky objects, but the total mass of all asteroids combined is less than 4% of the Moon's mass. If you were somehow flying through the asteroid belt, you wouldn't see asteroids everywhere like in movies. The distances between them are enormous. You'd have to aim carefully to hit one. Ceres, the largest object in the asteroid belt, is interesting. It's round, shaped by its own gravity, which is why it's classified as a dwarf planet. Ceres has a diameter of about 588 miles, about as wide as Texas. NASA's Dawn spacecraft visited Ceres from 2015 to 2018 and found evidence of a subsurface ocean. Ceres might have more fresh water than all of Earth's lakes and rivers combined. Jupiter dominates the outer solar system. It's so massive that its gravity affects the orbits of comets and asteroids throughout the solar system. Jupiter acts like a cosmic vacuum cleaner, attracting and capturing many objects that might otherwise threaten the inner planets. Some scientists think Jupiter's presence has been crucial for Earth's development. By reducing the number of large impacts Earth experienced, Jupiter might have made it possible for complex life to evolve here. Jupiter's most famous feature is the Great Red Spot, a storm larger than Earth that's been raging for at least 400 years. Wind speeds at the edges of the storm reach about 400 miles per hour. The storm is slowly shrinking, though. 100 years ago, it was about 3 times wider than Earth. Now, it's only about 1.3 times wider. If the shrinking continues, the Great Red Spot might disappear within our lifetimes. Jupiter has at least 95 moons, and more are being discovered regularly as our telescopes improve. The 4 largest moons, called the Galilean moons, are worlds in their own right. Io is the most volcanically active body in the solar system. Its surface is constantly being resurfaced by volcanic eruptions. Europa has a smooth, icy surface crisscrossed with cracks. Beneath the ice is likely a global ocean that could contain twice as much water as Earth's oceans. Ganymede is the largest moon in the solar system, even bigger than Mercury. And Callisto is heavily cratered with one of the oldest surfaces in the solar system. Saturn is perhaps the most visually striking planet, thanks to its magnificent ring system. The rings are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. The rings extend from about 4,300 miles to about 75,000 miles above Saturn's cloud tops. But they're remarkably thin, in most places only about 30 feet thick. No one knows exactly how old Saturn's rings are. They might have formed when Saturn did 4.6 billion years ago, or they might be much younger, perhaps only a few 100 million years old, formed when a moon was torn apart by Saturn's gravity. Scientists are still debating this question. Saturn has at least 146 known moons. The largest, Titan, is bigger than Mercury. Titan is the only moon in the solar system with a thick atmosphere. In fact, Titan's atmosphere is thicker than Earth's. The surface pressure is about 1.5 times Earth's sea level pressure. Titan's atmosphere is mostly nitrogen, like Earth's, but it also contains methane. Titan has liquid on its surface, but not water. It's too cold for that. Instead, Titan has lakes and seas of liquid methane and ethane. These hydrocarbons rain from the sky, carve river channels, and collect in low-lying areas. Titan is the only place in the solar system besides Earth where we've confirmed stable bodies of surface liquid. Another fascinating moon is Enceladus. This small moon, only about 313 miles across, has geysers at its south pole that shoot water ice hundreds of miles into space. The water comes from a subsurface ocean. The Cassini spacecraft flew through these geysers and detected organic molecules, the building blocks of life. Enceladus is now considered one of the best places in the solar system to search for life. Uranus is unusual because it's tilted on its side. Its axis of rotation is tilted about 98 degrees from vertical. This means its poles sometimes point almost directly at the sunday during Uranus's summer. One pole experiences continuous sunlight for 42 years. During winter, it experiences continuous darkness for 42 years. The planet's equator, meanwhile, has more normal day-night cycles. No one knows why Uranus is tilted so dramatically. The most likely explanation is that early in the solar system's history, the planet was hit by a large object that knocked it over. This collision might also explain why its magnetic field is tilted and offset from the planet's center. Neptune is the farthest planet from the Sunday. It's so far away that it takes about 165 Earth years to complete one orbit. The planet was discovered in 1846, which means it has completed less than 2 full orbits since we first spotted it. Wind speeds on this distant world reach up to 1,200 miles per hour, the fastest in the solar system. These extreme winds create large storms similar to Jupiter's Great Red Spot. Voyager 2 observed a storm called the Great Dark Spot in 1989. But when the Hubble Space Telescope looked at the planet in 1994, the Great Dark Spot had disappeared and new storms had formed in its place. The weather here changes quickly and unpredictably. At least 16 known moons orbit this ice giant. The largest, Triton, is unusual because it orbits backward compared to the planet's rotation. This retrograde motion suggests Triton wasn't formed alongside its parent world, but was captured from the Kuiper Belt. The moon is slowly spiraling inward. In about 3.5 billion years, it will either crash into its host planet or break apart from tidal forces, forming a ring system around the world. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies left over from the solar system's formation. Pluto is the most famous Kuiper Belt object. It was considered the 9th planet from its discovery in 1930 until 2006, when astronomers redefined what constitutes a planet. Pluto didn't make the cut because it hasn't cleared its orbit of other debris. Pluto is small, only about 1,473 miles across. But it's fascinating. It has 5 known moons, the largest being Charon, which is about half Pluto's size. Pluto and Charon are so close in size that they're sometimes called a binary system. They orbit a point in space between them, rather than Charon simply orbiting Pluto. NASA's New Horizons spacecraft flew past Pluto in July 2015, giving us our first close-up views. The images revealed a complex world, with mountains made of water, ice, vast plains of frozen nitrogen, and a thin atmosphere that extends much farther than expected. Pluto has a large, heart-shaped region called Tumbor Regio, named after Clyde Tombaugh, who discovered Pluto in 1930. There are other large Kuiper Belt objects. Eris, Makemake, and Haumea are all classified as dwarf planets. These objects show us that the outer solar system is more populated than we once thought. There might be thousands of dwarf planets in the Kuiper Belt, though most are too small and faint to detect with current telescopes. Beyond the Kuiper Belt is the Oort cloud, though no object in the Oort cloud has ever been directly observed. We know it exists because of comets. Long-period comets, those that take hundreds or thousands of years to orbit the Sun, come from the Oort cloud. When a passing star's gravity disturbs an Oort cloud object, it can fall toward the inner solar system, becoming a comet. The Oort cloud is enormous. It extends from about 2,000 AU to 100,000 AU from the Sunday. That's nearly 2 light years. The Oort cloud is so far away that the Sun's gravity barely holds onto it. A strong gravitational disturbance could pull objects free. This vast region marks the true edge of the solar system. Beyond the Oort cloud, the Sun's influence becomes negligible. Space becomes interstellar, the realm between stars. And in all this vast volume, Earth is one small rocky planet, 8,000 miles across, orbiting 1.0 AU from the Sunday. The solar system extends for trillions of miles, and Earth occupies only a tiny fraction of that space. Now let's leave the solar system and venture out to the nearest stars. This is where distances become so large that our usual measurements stop making sense. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It's about 4.24 light-years away. A light-year is the distance light travels in 1 year, which is about 5.88 trillion miles. So Proxima Centauri is about 25 trillion miles away. Here's a way to visualize this scale. Remember how the Sun is 93 million miles from Earth? Proxima Centauri is about 268,000 times farther away than the Sunday. If the distance from Earth to the Sun was 1 inch, the distance to Proxima Centauri would be about 4 miles. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object. It's been traveling for over 47 years and is now about 15 billion miles from Earth, moving at about 38,000 miles per hour. At that speed, Voyager would still need 73,000 years to reach Proxima Centauri, and it's not even aimed that direction. Even with hypothetical future technology, if we could build a spacecraft that traveled at 10% the speed of light, which is far beyond anything we can currently do, it would still take over 42 years to reach Proxima Centauri. The distances between stars are genuinely, almost incomprehensibly vast. And here's the thing. Proxima Centauri is our closest neighbor. Most stars are much farther away. Sirius, the brightest star in our night sky, is about 8.6 light-years away. Betelgeuse, the red giant in the constellation Orion, is roughly 700 light-years away. And these are still relatively close by cosmic standards. At these scales, Earth doesn't just shrink, it vanishes completely. If you were at Proxima Centauri looking back toward our solar system, you wouldn't be able to see Earth at all, even with a powerful telescope. The Sun would be visible as a bright star, but Earth would be lost in its glare, a tiny dot too close and too faint to detect. Let me tell you more about Proxima Centauri to help you understand what it means to be at the nearest star. Proxima Centauri is a red dwarf, the most common type of star in the galaxy. It's much smaller and cooler than the Sunday. Its diameter is only about 129,000 miles, roughly 14% of the Sun's diameter. It has only about 12% of the Sun's mass. Because Proxima Centauri is so small and cool, it burns its fuel very slowly. It will keep shining for trillions of years, long after the Sun has died. In fact, no red dwarf anywhere in the universe has ever died of old age. The universe isn't old enough yet. Every red dwarf that has ever formed is still shining today. Proxima Centauri is also a flare star. It regularly produces powerful flares, sudden releases of energy that can temporarily increase its brightness. These flares would be bad news for any planets hoping to host life. The radiation from a flare could strip away a planet's atmosphere or sterilize its surface. Interestingly, Proxima Centauri does have at least 2 known planets. Proxima Centauri b orbits in the star's habitable zone, the region where liquid water could exist on a planet's surface. But given the flares and radiation, life there seems unlikely. Still, it's fascinating that the nearest star to us has planets. Proxima Centauri is part of a triple star system with Alpha Centauri A and Alpha Centauri b. All 3 stars are gravitationally bound, forming a single system. The Alpha Centauri system has fascinated people for generations. In reality, we have no current technology that could send humans there within a human lifetime. Beyond Alpha Centauri, the next nearest star is Barnard's star, about 6 light-years away. Sirius, the brightest star in Earth's night sky, is about 8.6 light-years away. Betelgeuse, one of the most famous stars, is about 700 light-years away. It's a red supergiant, so large that if you placed it where the Sun is, it would extend past the orbit of Mars. All these stars are part of our stellar neighborhood. And yet, the distances between us and them are so vast that we'll probably never visit them. The light you see when you look at Betelgeuse left that star around the time the Crusades were ending on Earth. And our planet? At these distances, Earth has disappeared from view. The solar system itself is just a point of light, and Earth is far too small and faint to be visible within that point. Let's zoom out further. All the stars we can see with our naked eye, every single one, belongs to our galaxy, the Milky Way. The Milky Way is a spiral galaxy containing somewhere between 100 billion and 400 billion stars. Our Sun is just one of them. The Milky Way is about 100,000 light-years across. Remember, Proxima Centauri is about 4.24 light-years away. The width of our galaxy is about 24,000 times that distance. If the distance to Proxima Centauri was 1 inch, the Milky Way would be about 2,000 feet across. That's taller than most skyscrapers. Our Sun sits about 26,000 light-years from the galactic center. We're in a minor spiral arm called the Orion Spur, about halfway out from the center. We're not in the middle of anything special. We're in the suburbs of the galaxy, in a relatively quiet region where stars aren't too densely packed. At this scale, Earth's presence in the cosmos becomes conceptually different. Even our entire solar system is just a tiny point. The Sun, which seemed so massive compared to Earth, is now just one ordinary star among hundreds of billions. And Earth is far too small to even register. Imagine compressing our galaxy into a structure 100 feet across our entire solar system would measure thinner than a human hair's width. And Earth would be far, far smaller than that. At this scale, Earth wouldn't just be invisible. It would be smaller than an atom in the model. The Milky Way is a barred spiral galaxy. This means it has a central bar-shaped structure made of stars, with spiral arms extending from the ends of the bar. Our Sun is located in the Orion Spur, which is actually a minor arm connecting two major spiral arms called the Sagittarius arm and the Perseus arm. The galaxy rotates, but not like a solid wheel. Different parts rotate at different speeds. Near the center, stars orbit faster. Farther out, they orbit more slowly. Our Sun takes about 225 million years to complete one orbit around the galactic center. This is called a galactic year, or cosmic year. Think about that. In the time it takes for our Sun to go around the galaxy once, entire species rise and fall on Earth. The last time the Sun was at this point in its orbit, dinosaurs were just beginning to emerge. The time before that, the supercontinent Pangaea was still intact. Earth has been around for about 20 galactic years. The universe has existed for about 60 galactic years. These timescales are almost incomprehensible. The Milky Way has several distinct regions. At the center is the galactic bulge, a dense concentration of old stars. This region is about 10,000 light-years across. The stars here are packed much more densely than in our neighborhood. If you lived on a planet near the galactic center, your night sky would be filled with thousands of bright stars, making the night almost as bright as twilight on Earth. At the very center of the galactic bulge sits Sagittarius A star, the supermassive black hole. We'll discuss more later. This black hole has a mass of about 4 million times the mass of our Sunday. It's relatively quiet now, but it occasionally flares up when gas or even a star falls into it. Around the galactic center are the spiral arms. These are regions where gas and dust are compressed, triggering star formation. The spiral arms appear bright because they contain lots of young, hot blue stars. These massive stars live fast and die young, rarely lasting more than a few million years. By the time they die, they've barely moved from where they were born, so they stay in the spiral arms. Our Sun, being an older, more stable star, has had time to drift away from the spiral arm where it formed. We're now between spiral arms, in a relatively quiet region. This is probably a good thing for life on Earth. Spiral arms are violent places, with lots of supernovae and intense radiation. Being between the arms gives Earth a safer environment. Surrounding the spiral structure is the galactic halo, a roughly spherical region containing old stars and globular clusters. The halo extends about 130,000 light-years from the galactic center. The stars in the halo are among the oldest in the galaxy, formed when the Milky Way was just beginning to take shape. The halo also contains dark matter. We can't see dark matter directly, but we can detect its gravitational effects. The Milky Way's dark matter halo extends even farther than the visible halo, possibly out to 600,000 light-years or more. Most of the Milky Way's mass is actually dark matter, not stars and gas. The Milky Way isn't isolated. It has numerous satellite galaxies orbiting it. The two most famous are the Large and Small Magellanic Clouds. Both are being slowly torn apart by the Milky Way's gravity, and will eventually be completely absorbed. There are dozens of other smaller satellite galaxies. Most are dwarf galaxies containing only a few million stars. These satellites are important for understanding how galaxies grow. Large galaxies like the Milky Way form through mergers. The satellites we see today are the leftovers that haven't merged yet. The Milky Way is also moving through space toward the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will merge into a single large elliptical galaxy containing roughly 1.5 trillion stars in total. The Milky Way isn't uniform. Stars are distributed in different ways throughout the galaxy. Near the center, stars are packed more densely. In the spiral arms, where we live, stars are more spread out. The nearest star-forming region to us is the Orion Nebula, about 1,344 light-years away. It's a cloud of gas and dust where new stars are being born. The nebula is about 24 light-years across. Inside it, hundreds of stars are forming from collapsing clouds of hydrogen. Star-forming regions like this show us how stars and planets come to be. About 4.6 billion years ago, our Sun formed in a similar nebula. The Sun, and probably hundreds of other stars, condensed from the same cloud of gas. Those sibling stars have long since drifted apart, scattered across the galaxy by the motions of stars and the rotation of the Milky Way. There are also stellar clusters, groups of stars that form together and remain gravitationally bound. The Pleiades, also known as the Seven Sisters, is an open cluster about 444 light-years away. It contains over 1,000 stars, all of which formed from the same gas cloud about 100 million years ago. The cluster is about 8 light-years across. Globular clusters are even more impressive. These are dense, spherical collections of hundreds of thousands or even millions of stars. M13, also known as the Great Globular Cluster in Hercules, contains about 300,000 stars packed into a region about 145 light-years across. At the center of M13, stars are so densely packed that if you lived on a planet there, your night sky would be filled with thousands of stars as bright as Venus appears in our sky. M13 is about 22,200 light-years from Earth. At that distance, even powerful telescopes struggle to distinguish individual stars in the cluster's core. Everything blurs together into a dense ball of light. And Earth? At this scale, Earth is beyond insignificant. The entire planet would be so small that no measurement could capture how tiny it is compared to structures like M13. We're talking about a difference in scale so vast that analogies start to fail. At the center of the Milky Way sits something remarkable. A supermassive black hole called Sagittarius A. This black hole has a mass of about 4 million times the mass of our Sun. It's about 17 times the size of the Sun in diameter, which might not sound that big, but remember, this is a black hole. All that mass is compressed into a relatively small space. The region around Sagittarius A is chaotic. Stars orbit the black hole at incredible speeds. One star, called S2, orbits the black hole once every 16 years at speeds reaching 5% of the speed of light. At its closest approach, S2 comes within about 11 billion miles of the black hole. That's about the distance from the Sun to Saturn. The center of the galaxy is also bright. Not in visible light, because dust blocks our view, but in infrared and radio waves. There's a lot of activity happening there. Gas falls toward the black hole, heating up and emitting radiation. Stars are being born and dying at higher rates than in the outer regions of the galaxy. Most galaxies have supermassive black holes at their centers. These black holes play a crucial role in galaxy formation and evolution. They can affect star formation across the entire galaxy through the energy they release. In some galaxies, the central black hole is actively feeding, consuming vast amounts of gas and producing jets of matter and energy that extend for thousands of light years. Our galaxy's black hole is relatively quiet right now. It's not actively feeding on large amounts of material. But about 6 million years ago, it appears to have been much more active. Astronomers have found evidence of enormous bubbles of energy extending above and below the galactic plane, likely created by a past period of intense activity from Sagittarius A. But let's not lose sight of our main question. Earth's position in this structure is 26,000 light-years from this central region. We're far away, safely distant from the chaos at the galactic core. And at this scale, Earth is so unimaginably small that it defies description. The Milky Way isn't alone in space. It has neighbors. About 50 galaxies, including the Milky Way, form what astronomers call the local group. This is our immediate cosmic neighborhood. The largest member of the local group is Andromeda, also called M31. Andromeda contains about 1 trillion stars, more than twice what the Milky Way has. It's about 220,000 light-years across, more than twice the Milky Way's diameter, and it's on a collision course with us. In about 4.5 billion years, Andromeda and the Milky Way will merge into a single large galaxy. Don't worry about the collision. When galaxies merge, the stars are so far apart that actual collisions between stars are incredibly rare. The galaxies will pass through each other, their gravity pulling them back together, until eventually they settle into a single, large, elliptical galaxy. By then, the Sun will probably be dead anyway. So humans, if we still exist, will have long since left Earth, or won't be around to see it. The next largest member of the local group is Triangulum, or M33. It contains about 40 billion stars and is about 60,000 light-years across. It's smaller than the Milky Way, but still a respectable galaxy in its own right. The rest of the local group consists mostly of dwarf galaxies. These are small collections of a few billion stars or less. The Large Magellanic Cloud, which orbits the Milky Way, contains about 10 billion stars. The Small Magellanic Cloud has a few billion. Both are visible from the southern hemisphere as fuzzy patches in the night sky. The local group spans about 10 million light-years. That sounds enormous, and it is. But it's just the beginning. The local group is one small collection of galaxies in a much larger structure. The local group is part of the Virgo supercluster, an enormous collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo supercluster contains at least 100 galaxy clusters and groups with a total of somewhere around 100 trillion stars. The dominant structure in the Virgo supercluster is the Virgo cluster itself, located about 54 million light-years from us. This cluster contains between 1,200 and 2,000 galaxies. Some of these galaxies are enormous, far larger than the Milky Way. M87, a giant elliptical galaxy at the heart of the Virgo cluster, contains about 1 trillion stars. It's roughly 120,000 light-years across, similar in diameter to the Milky Way, but much more massive. M87 is also famous for being the first galaxy where we directly imaged a black hole. In 2019, the Event Horizon Telescope collaboration released an image showing the shadow of M87's supermassive black hole, which has a mass about 6.5 billion times the mass of the Sunday. Consider this magnitude for a moment. The Milky Way seemed enormous, but it's just one galaxy in a cluster that contains thousands. And that cluster is just one part of a supercluster that contains hundreds of clusters. If we made a scale model where the Milky Way was the size of a coin, the Virgo supercluster would be about the size of a large city. Everything you've heard about up to this point, the sun, the solar system, the distances between stars, the Milky Way itself, all of that would fit on a coin in this model. And Earth would be far smaller than any particle you could see with a microscope. In 2014, astronomers discovered something even larger than the Virgo supercluster. They found that the Virgo supercluster is just a small part of an even more massive structure called Laniakea. The name comes from Hawaiian and means immeasurable heaven. Laniakea is a supercluster of superclusters. It contains about 100,000 galaxies spread across 520 million light-years. All these galaxies, including our Milky Way, are slowly moving toward the center of Laniakea, pulled by the combined gravity of all that mass. The center of Laniakea, the point toward which everything is flowing, is called the Great Attractor. This is a region of space with such enormous gravitational pull that it's drawing in thousands of galaxies. The Great Attractor itself sits behind the plane of the Milky Way from our perspective, which means dust and gas in our own galaxy block our view of it. For decades, astronomers knew something massive was there because they could measure its gravitational effects, but they couldn't see it directly. Using different types of light, radio waves, infrared, X-rays, astronomers have pieced together what the Great Attractor is. It's not a single object, but a region containing several massive galaxy clusters. The Norma cluster is one of the largest structures in that region. But even the Great Attractor isn't the whole story. Recent observations suggest there's something even more massive beyond Laniakea pulling it. The Shapley supercluster, located about 650 million light-years away, contains thousands of galaxies and has a total mass of about 10,000 trillion times the mass of the Sunday. The combined gravity of the Shapley supercluster appears to be pulling Laniakea and everything in it. At this scale, the Milky Way has become just one of 100,000 galaxies in Laniakea. And Earth? Picture the observable universe scaled to Earth's dimensions. The Milky Way would shrink below atomic scale, and Earth itself would cease to exist at any measurable size. If Laniakea were compressed to match Earth's dimensions, the Milky Way would barely exceed a sand grain's volume, and Earth would vanish into quantum scales. When you map out the distribution of galaxies across the universe, a pattern emerges. Galaxies aren't randomly scattered. Instead, they cluster along filaments and walls, forming a cosmic web. Between these filaments are vast empty regions called voids. This structure exists because of how the universe evolved. In the very early universe, tiny density fluctuations existed in the distribution of matter. Some regions were slightly denser than average, others slightly less dense. Over billions of years, gravity amplified these differences. Dense regions attracted more matter, becoming denser. Less dense regions lost matter to their surroundings, becoming voids. The result is the cosmic web we see today. Filaments of galaxies stretch across hundreds of millions of light years, surrounding voids that are nearly empty. Laniakea is one filament in this web. There are many others. One of the largest known structures is the Sloan Great Wall, discovered in 2003. This is a wall of galaxies stretching about 1.37 billion light-years. It contains tens of thousands of galaxies arranged in a relatively thin sheet. If the Milky Way were the size of a coin, the Sloan Great Wall would stretch for miles. Another large structure is the Hercules Corona Borealis Great Wall, which might be the largest structure ever discovered. It stretches about 10 billion light-years across. That's about 73% of the radius of the observable universe. Structures this large actually created problems for cosmologists, because according to our models, there shouldn't have been enough time for something this large to form. Between these structures are the voids. The largest known void is the KBC void, about 2 billion light-years across. Inside this void, there are very few galaxies. It's not completely empty, but the density of galaxies is much lower than in surrounding regions. If you were somehow in the center of this void and looked out, the nearest significant galaxy clusters would be about 1 billion light-years away. The universe would seem much emptier from that vantage point. These voids make up about 80% of the universe's volume. Most of space is empty. The galaxies, superclusters, and filaments occupy only a small fraction of the total volume. The universe is like a vast ocean, with occasional islands of matter scattered throughout. And our world's significance here? Earth sits in one of these islands in a galaxy that's part of a filament in this cosmic web. At the scale of the cosmic web, Earth doesn't just become invisible. It becomes inconceivable. The difference in size between Earth and the cosmic web is so vast that human minds struggle to grasp it. The observable universe is the part of the universe we can theoretically see. It's limited by the speed of light and the age of the universe. Light from anything farther away than a certain distance hasn't had time to reach us yet. The universe is about 13.8 billion years old. You might think this means we can see 13.8 billion light-years in every direction, but the universe has been expanding the whole time. Space itself has been stretching, so a galaxy that emitted light 13 billion years ago has moved much farther away during the time its light has traveled toward us. The result is that the observable universe is about 93 billion light-years in diameter. That's the maximum distance from which light has had time to reach us, accounting for the expansion of space. Within this observable universe, astronomers estimate there are about 2 trillion galaxies. 2 trillion, each containing anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. For comparison, if every star was represented by a grain of sand, you would need several Olympic-sized swimming pools to hold them all. And Earth? Earth would be so unimaginably small that no comparison captures it. You could fit so many Earths into the observable universe that the number becomes meaningless. With the observable universe scaled to Earth's dimensions, the Milky Way shrinks beneath subatomic particles, and Earth transcends measurability entirely. It would be smaller than the fundamental particles that make up atoms. The observable universe is just what we can see. The actual universe is almost certainly much larger. How much larger? We don't know. It might be a few times larger than what we can see. It might be thousands of times larger. It might be infinite. If the universe is infinite, then the observable universe is basically nothing. No matter how large 93 billion light-years seems, it's still 0% of infinity. And Earth would be even less significant in an infinite universe than it already is in the observable universe. Some theories in physics suggest the universe might be part of a multiverse, an infinite collection of universes. According to eternal inflation theory, the Big Bang wasn't a single event, but something that happens constantly, creating bubble universes that spawn more bubble universes. Our universe would be just one bubble in an infinite foam. Other interpretations of quantum mechanics suggest that every time a quantum event has multiple possible outcomes, the universe splits into multiple branches, with each outcome occurring in a different branch. This would create an infinite number of parallel universes. These ideas are speculative. We have no way to observe other universes, so testing these theories is extremely difficult. But they arise naturally from well-established physics, which is why many physicists take them seriously. If the multiverse exists, then our entire universe, with its 93 billion light-year diameter and 2 trillion galaxies, is just one universe among infinitely many. And Earth? Earth becomes even more vanishingly insignificant. Let's zoom back in for a moment and look more carefully at Earth's place in our solar system. Because even in our immediate neighborhood, Earth's smallness becomes clear. Mercury, the closest planet to the Sun, is about 3,032 miles in diameter. That's only about 38% of Earth's diameter. Mercury's volume could fit inside Earth about 18 times. Mercury is a tiny, scorched world, its surface temperatures swinging from about 800 degrees Fahrenheit during the day to minus 290 degrees at night. Venus is closer to Earth in size. It has a diameter of about 7,521 miles, about 95% of Earth's diameter. Venus is often called Earth's sister planet because of the similar size. But the surface conditions couldn't be more different. The atmosphere is thick with carbon dioxide, the pressure is about 90 times higher than Earth's, and the temperature averages about 900 degrees Fahrenheit. It's hot enough to melt lead. Mars is smaller than Earth, with a diameter of about 4,212 miles. That's about 53% of Earth's diameter. About 7 Mars-sized planets could nest inside Earth's volume. Mars has 2 tiny moons, Phobos and Deimos, that are probably captured asteroids. Phobos is only about 14 miles across. If you stood on Phobos, Mars would dominate half the sky, a massive red sphere looming overhead. Jupiter is where things get truly large. With a diameter of about 86,881 miles, Jupiter could span about 11 Earths across its diameter. But volume is what really matters. Jupiter's volume is so immense that 1,321 Earths would barely fill it. Jupiter is so large that all the other planets combined have less mass than Jupiter alone. Jupiter has at least 95 known moons. The 4 largest, called the Galilean moons after Galileo, who discovered them in 1610, are Io, Europa, Ganymede, and Callisto. Ganymede is the largest moon in the solar system, even bigger than Mercury. It has a diameter of about 3,273 miles. Europa is particularly interesting because beneath its icy surface is likely a global ocean that might contain twice as much water as all of Earth's oceans combined. Saturn is nearly as large as Jupiter, with a diameter of about 72,367 miles. Saturn could swallow 764 Earth-sized worlds within its bulk. Saturn has at least 146 known moons. The largest, Titan, has a diameter of about 3,200 miles. Titan is the only moon in the solar system with a thick atmosphere, and it has liquid lakes and seas on its surface. Not water, though. The lakes are made of liquid methane, and ethane because Titan is so cold. Uranus has a diameter of about 31,518 miles. The volume of Uranus equals roughly 63 planets the size of ours. Uranus is tilted on its side, with its axis of rotation nearly parallel to its orbital plane. This means that for part of its orbit, one pole points almost directly at the Sun, while the other is in complete darkness. Each season on Uranus lasts about 21 Earth years. Neptune, the farthest planet from the Sun, has a diameter of about 30,599 miles. Neptune's interior could accommodate 57 Earth-mass bodies. Neptune is incredibly windy, with wind speeds reaching up to 1,200 miles per hour. These are the fastest winds measured on any planet in the solar system. Even in our own solar system, Earth is small. Jupiter absolutely dwarfs it. Saturn could swallow it whole hundreds of times over, and these are just planets. When you include the Sun, which dominates the solar system with 99.86% of its total mass, Earth becomes even smaller. Our solar system isn't just planets. It's also filled with moons, asteroids, comets, and other small bodies. And many of these are smaller than Earth, which gives us perspective on what small really means. Earth has one moon. Our moon has a diameter of about 2,159 miles, about 27% of Earth's diameter. The moon is actually quite large relative to its planet. Most moons in the solar system are tiny compared to the planets they orbit. But Earth and the moon are sometimes described as a double planet system because the moon is proportionally so large. Mars has two moons, but they're both tiny. Phobos, the larger one, is only about 14 miles across. Deimos is even smaller, at about 7.5 miles. These moons are likely captured asteroids rather than objects that formed alongside Mars. Jupiter's system is impressive. Besides the 4 large Galilean moons, Jupiter has dozens of smaller moons. Many are less than 6 miles across. Some are probably captured comets or asteroids. The gravitational pull of Jupiter is so strong that it captures passing objects, adding them to its collection of satellites. Saturn's moon system is equally fascinating. Besides Titan, which is larger than Mercury, Saturn has Enceladus, a small icy moon about 313 miles in diameter. Enceladus has geysers at its south pole that shoot water ice into space. This suggests there's a liquid water ocean beneath the ice, making Enceladus another candidate for potential life in our solar system. The asteroid belt contains thousands of rocky objects. The largest, Ceres, has a diameter of about 588 miles. That's only about 7% of Earth's diameter. Most asteroids are much smaller. Vesta, the second largest, is about 326 miles across. Most asteroids are just a few miles or even a few hundred feet across. Beyond Neptune, in the Kuiper belt, there are thousands of icy objects. Pluto, once considered the 9th planet, has a diameter of about 1,473 miles. That's about 18.5% of Earth's diameter. Pluto is now classified as a dwarf planet, one of several large Kuiper Belt objects. All these small objects remind us that Earth, while small compared to the gas giants, is actually one of the larger solid objects in the solar system. Most moons and asteroids are far smaller than Earth. Earth is a decent-sized rocky planet, but in the context of the universe, even the gas giants are tiny. Since the first exoplanet was confirmed in 1992, astronomers have discovered over 5,500 planets orbiting other stars. These discoveries have revealed incredible diversity in planetary systems. Some exoplanets are enormous. Hot Jupiters are gas giant planets that orbit very close to their stars. These planets can be several times more massive than Jupiter. HD 189-733b, for example, has a mass about 13 times that of Jupiter. It orbits so close to its star that its year is only about 3 Earth days long. Other exoplanets are tiny. Kepler 37b is about the size of Earth's moon, with a diameter of only about 2,400 miles. It orbits its star every 13 days. Some exoplanets are in the habitable zone, the region around a star where liquid water could exist on a planet's surface. Kepler 452b, for example, orbits in its star's habitable zone and is about 60% larger than Earth. It's located about 1,800 light-years away. We'll never visit it, but it's interesting to know such planets exist. The variety of exoplanets shows us that planetary systems come in all configurations. Some stars have multiple planets packed close together. Others have planets in highly elliptical orbits. Some planets orbit binary star systems with 2 suns in the sky. The diversity is stunning. But here's what matters for our discussion. Earth is just one planet among thousands we've discovered, and likely billions that exist in the Milky Way alone. Earth isn't unique in being a planet. It's not even unique in being a rocky planet roughly our size. There are probably millions or billions of Earth-sized rocky planets in the Milky Way. Since the first exoplanet was confirmed in 1992, astronomers have discovered over 5,500 planets orbiting other stars. These discoveries have revealed incredible diversity in planetary systems. Some exoplanets are enormous. Hot Jupiters are gas giant planets that orbit very close to their stars. These planets can be several times more massive than Jupiter. HD 189-733b, for example, has a mass about 13 times that of Jupiter. It orbits so close to its star that its year is only about 3 Earth days long. Other exoplanets are tiny. Kepler 37b is about the size of Earth's moon, with a diameter of only about 2,400 miles. It orbits its star every 13 days. Some exoplanets are in the habitable zone, the region around a star where liquid water could exist on a planet's surface. Kepler 452b, for example, orbits in its star's habitable zone and is about 60% larger than Earth. It's located about 1,800 light-years away. We'll never visit it, but it's interesting to know such planets exist. The variety of exoplanets shows us that planetary systems come in all configurations. Some stars have multiple planets packed close together. Others have planets in highly elliptical orbits. Some planets orbit binary star systems with 2 suns in the sky. The diversity is stunning. But here's what matters for our discussion. Earth is just one planet among thousands we've discovered, and likely billions that exist in the Milky Way alone. Earth isn't unique in being a planet. It's not even unique in being a rocky planet roughly our size. There are probably millions or billions of Earth-sized rocky planets in the Milky Way. What might be unique about Earth is that it has life. As far as we know, Earth is the only planet where life exists. We might discover microbial life elsewhere in our solar system, perhaps on Mars or in the oceans of Europa or Enceladus. And there might be countless other planets with life elsewhere in the galaxy or universe. But right now, Earth is the only confirmed example. This makes Earth precious, even if it's small. Size isn't everything. What matters is what's on a planet, not just how big it is. To further understand Earth's scale, let's look at stars. Because stars vary enormously in size, and comparing them to Earth puts things in perspective. The Sun is a fairly average star. It's what astronomers call a G-type main sequence star, or yellow dwarf. Its diameter is about 864,000 miles. About 109 Earths could span the Sun's diameter, and approximately 1.3 million Earth-sized spheres could fill its volume. But many stars are much smaller than the Sunday. Red dwarfs are the most common type of star in the galaxy. Proxima Centauri, the nearest star to us, is a red dwarf with a diameter of about 129,000 miles. That's only about 15% of the Sun's diameter. About 8.5 Earths could line up across Proxima Centauri's diameter. The smallest known star is EBLM J0555-57 AB, with a diameter of about 68,000 miles. That's only about 8% of the Sun's diameter. This star is barely large enough to sustain hydrogen fusion in its core. Any smaller, and it would be a brown dwarf, a failed star that never got hot enough to start fusion. On the other end of the scale are the giants and hypergiants. Betelgeuse, a red supergiant in the constellation Orion, has a diameter of about 617 million miles. That's about 700 times larger than the Sunday. If you placed Betelgeuse where the Sun is, it would extend past the orbit of Mars. Earth would be deep inside the star, vaporized instantly. But Betelgeuse isn't the largest. UY Scuti, one of the largest known stars, has a diameter of about 1.7 billion miles. That's about 1,900 times larger than the Sunday. If UY Scuti replaced the Sun, it would extend past the orbit of Saturn. This stellar giant's volume is so staggering that approximately 6.5 trillion Earth-sized spheres could occupy the same space. That number is so large, it's almost meaningless. These comparisons show that Earth isn't just small compared to the Sunday, it's tiny compared to even modest stars, and incomprehensibly tiny compared to the largest stars. A red dwarf, which is a small star, is still enormously larger than Earth. UY Scuti is so much larger than Earth that the comparison becomes absurd. When stars die, they leave behind remnants. These remnants are often small but incredibly dense. Looking at these objects gives us yet another perspective on Earth's scale. When a star like the Sun dies, it swells into a red giant, then sheds its outer layers, leaving behind a white dwarf. A white dwarf is the exposed core of the star, incredibly hot but small. A typical white dwarf has a diameter of about 6,200 miles, only about 80% of Earth's diameter. But here's the remarkable thing. Even though a white dwarf is similar in size to Earth, it contains about half the mass of the Sunday. All that mass is compressed into Earth-sized volume. The density is about 1 million times the density of Earth. A teaspoon of white dwarf material would weigh about 5 tons on Earth. When more massive stars explode as supernovae, they can leave behind neutron stars. These are even more extreme. A neutron star might be only about 12 miles across, about the size of a city. But it contains 1.4 to 2 times the mass of the Sunday. The density is so extreme that a teaspoon of neutron star material would weigh about 4 billion tons. The most massive stars can collapse into black holes. These are regions of space where gravity is so strong that nothing can escape, not even light. The black hole at the center of the Milky Way, Sagittarius A, has a mass about 4 million times the mass of the Sunday, but its event horizon, the boundary beyond which nothing can escape, is only about 17 times the diameter of the Sunday. That's tiny for something so massive. M87's black hole, which was imaged in 2019, has a mass about 6.5 billion times the mass of the Sunday. Its event horizon is about 23.6 billion miles across. That's enormous, about 250 times the distance from the Sun to Earth. But it's still small compared to the galaxy it sits in. These stellar remnants show us that size and mass don't always correlate. A white dwarf is smaller than Earth but more massive than the Sunday. A neutron star is the size of a city but contains more mass than the Sunday. These objects are dense beyond anything we encounter in everyday life. But they also remind us that Earth, even though it's small, is actually pretty big for a solid object. Most solid objects in the universe are smaller than Earth. Moons, asteroids, and stellar remnants tend to be smaller. Earth is a medium-sized rocky planet, and that's actually pretty substantial in the grand scheme of things. We've talked about the Milky Way, but let's look more carefully at galaxy sizes, because galaxies vary enormously, and understanding this helps us see where the Milky Way fits, which in turn helps us understand where Earth fits. Dwarf galaxies are the most common type. These contain anywhere from a few million to a few billion stars, and are typically only a few thousand light-years across. The Large Magellanic Cloud, which orbits the Milky Way, contains about 10 billion stars and is roughly 14,000 light-years across. The Small Magellanic Cloud is even smaller. Ultra-faint dwarf galaxies are the smallest galaxies known. Segway 1, for example, contains only about 1,000 stars and is a few hundred light-years across. It's barely a galaxy at all. It's more like a large star cluster. These small galaxies are everywhere. Every large galaxy is surrounded by dozens or hundreds of small satellite galaxies. The Milky Way has about 50 known satellites. Andromeda has similar numbers. These small galaxies are the leftover building blocks from galaxy formation. In the early universe, the first galaxies were all small. Over time, they merged to form larger galaxies. On the other end of the scale are the giant ellipticals. IC 10101 is about 6 million light-years across, 60 times larger than the Milky Way. It contains about 100 trillion stars. This galaxy grew by consuming other galaxies over billions of years. It sits at the center of a galaxy cluster, where its gravity allowed it to cannibalize its neighbors. M87 is another giant elliptical about 120,000 light-years across. It's similar in diameter to the Milky Way, but much more massive. It contains about 1 trillion stars and has a supermassive black hole at its center with a mass of 6.5 billion solar masses. These giant galaxies are rare. Most galaxies are dwarfs. The Milky Way, with its 100,000 light-year diameter and hundreds of billions of stars, is actually in the top 5% of galaxies by size. About 95% of all galaxies are smaller than the Milky Way. So the Milky Way is large by cosmic standards. But it's still dwarfed by the largest galaxies. And at the scale of galaxy clusters, superclusters, and the cosmic web, even the largest galaxies become small pieces in much larger structures. And our planet? In the context of galaxies, Earth completely disappears. The Milky Way is 100,000 light-years across. Earth is about 8,000 miles in diameter. The ratio between these sizes is so vast that Earth becomes essentially non-existent at galactic scales. Let's shift perspective and think about what Earth is made of, because understanding the structure of matter helps us understand scale in a different way. Earth is made of atoms. An atom is incredibly small. The diameter of a hydrogen atom, the simplest atom, is about 0.1 nanometers. That's 0.1 billionths of a meter. You could line up about 10 million hydrogen atoms across the width of a human hair. How many atoms are in Earth? Earth has a mass of about 6 trillion kilograms. Most of that mass is in the form of iron, oxygen, silicon, magnesium, and other elements. If we assume an average atomic mass, Earth contains roughly 1.3 times 10 to the 50 atoms. That's 13, followed by 49 zeros. That's an incomprehensibly large number. If you counted one atom per second, it would take you more than 10 times the age of the universe to count all the atoms in Earth. And Earth is just one planet. Imagine how many atoms are in the Sun, which is over 300,000 times more massive than Earth, or in the Milky Way, or in the observable universe. Atoms themselves have structure. At the center of an atom is a nucleus made of protons and neutrons. The nucleus is tiny, about 100,000 times smaller than the atom itself. If an atom were the size of a football stadium, the nucleus would be about the size of a marble at the center of the field. Despite being tiny, the nucleus contains almost all the atom's mass. Protons and neutrons are about 1,800 times more massive than electrons. So even though electrons occupy most of the atom's volume, they contribute very little to its mass. Protons and neutrons are themselves made of quarks. 3 quarks combine to make a proton or neutron. Quarks are fundamental particles as far as we know. They're not made of anything smaller. The point of all this is that matter, including Earth, has structure at many different scales. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks, and at each scale, there's mostly empty space. An atom is mostly empty space between the nucleus and the electrons. If you removed all the empty space from atoms, if you compressed Earth so that all its atoms were touching nucleus to nucleus, Earth would be about the size of a large building. All the matter in Earth, compressed to nuclear density, would fit in a sphere about 600 feet across. That's still a lot of material, but it's tiny compared to Earth's actual 8,000-mile diameter. This shows us that even solid objects like Earth are mostly empty space. The same is true throughout the universe. Stars, planets, galaxies, everything is mostly empty space. The universe is far emptier than it appears. Let's add another dimension to our understanding of Earth's scale. Not just how big it is in space, but how long it's existed in time. Earth formed about 4.54 billion years ago from the same disk of gas and dust that formed the Sun and the rest of the solar system. The early Earth was a molten ball, constantly bombarded by asteroids and comets. Over time, it cooled, developed a solid crust, and eventually gained an atmosphere and oceans. Life appeared relatively quickly after Earth became habitable. The oldest evidence of life dates back about 3.8 billion years. These were simple single-celled organisms, similar to modern bacteria. For most of Earth's history, life consisted only of these simple forms. Complex multicellular life didn't appear until about 600 million years ago. The Cambrian explosion about 540 million years ago saw a rapid diversification of life forms. Since then, life has evolved through many forms. Dinosaurs appeared about 230 million years ago and went extinct about 66 million years ago. Humans appeared only about 300,000 years ago. If you compressed Earth's entire history into a single year, with January 1st being Earth's formation and December 31st being today, life would appear in March. The Cambrian explosion would happen in mid-November. Dinosaurs would appear on December 13th and go extinct on December 26th. Humans would appear at 11:56 p.m. on December 31st. All of recorded human history would occupy the last 10 seconds of the year. But let's zoom out further. The universe is about 13.8 billion years old. Earth formed about 9.3 billion years after the Big Bang. So Earth has existed for only about 33% of the universe's history. The universe is about 3 times older than Earth. And the universe has a long future ahead of it. Current evidence suggests the universe will continue expanding forever. Stars will keep forming for trillions of years, though the rate of star formation will decline over time. Eventually, in about 100 trillion years, all the gas in galaxies will be used up and star formation will cease. The universe will enter what's called the degenerate era, where the only sources of light are long-lived red dwarf stars and slowly cooling white dwarfs. Even those will eventually fade. In about 1 quintillion years, that's 1 followed by 18 zeros, even the longest-lived stars will die. The universe will be filled only with stellar remnants, black holes, and perhaps some exotic objects we haven't discovered yet. Black holes themselves will eventually evaporate through a process called Hawking radiation. A supermassive black hole like the one at the center of the Milky Way will take about 10 to the 100 years to evaporate. That's 1 followed by 100 zeros. This is so far in the future that it's almost meaningless to contemplate. Earth's existence, then, is brief. 4.5 billion years out of a universe that's 13.8 billion years old and will last for trillions upon trillions more. Earth's time in the universe is like a single heartbeat in a human lifetime. No, it's even shorter than that. It's like a single heartbeat in the lifetime of the universe itself, which will last far longer than any human lifetime. Let's bring everything together now. We've looked at Earth from many angles. We've compared it to the Moon, the Sun, the solar system, nearby stars, the Milky Way, galaxy clusters, superclusters, and the cosmic web. We've looked at the structure of matter and the scale of time. Every comparison shows the same thing. Earth is small. Not just small, tiny, incomprehensibly tiny, when compared to the full scale of the universe. The observable universe is 93 billion light-years across. It contains about 2 trillion galaxies. Each galaxy contains anywhere from millions to trillions of stars. The total number of stars is about 200 billion trillion. Earth is 1 planet orbiting 1 star in 1 galaxy among 2 trillion galaxies. If you selected a random star in the observable universe, the chances of picking the Sun are 1 in 200 billion trillion. And even if you somehow picked the Sun, you'd then have to select Earth out of 8 planets, dozens of moons, and countless asteroids and comets. The chances of randomly selecting Earth out of all the objects in the observable universe are so small that the number is effectively 0. Earth is not just rare, it's vanishingly rare. But here's something to consider. The observable universe is just what we can see. The actual universe is larger. possibly infinitely larger. If it's infinite, then no matter how improbable something is, it will happen infinitely many times. There could be infinite copies of Earth out there, each with its own version of you reading this script. This is speculative, of course. We have no way to observe beyond the observable universe, but it's a reminder that even our most extreme estimates of scale might be underestimating the true size of everything that exists. In 1990, the Voyager 1 spacecraft, which had completed its primary mission and was heading out of the solar system, turned its camera back toward Earth and took a photograph. Earth appeared as a tiny pale blue dot, less than a pixel in size, suspended in a beam of sunlight. This photo, taken from about 3.7 billion miles away, is one of the most profound images ever captured. It shows Earth as it really is in the context of space, a tiny speck floating in an enormous void. The astronomer Carl Sagan reflected on this image in his book Pale Blue Dot. He wrote about how every human who ever lived out their entire life on that tiny speck. Every king and peasant, every hero and villain, every creator and destroyer of civilization, all of them lived on that dot. All our triumphs and tragedies, all our wars and peace, everything that has ever mattered to humanity happened on that barely visible speck. Sagan's point was that this perspective should change how we see ourselves and our world. The petty disagreements that divide us, the borders we fight over, the resources we compete for, all of it plays out on a stage so small that from a modest distance, it disappears entirely. This doesn't make our lives meaningless. If anything, it makes them more precious, because as far as we know, that pale blue dot is the only place in the universe where life exists. And conscious, intelligent life? That might be even rarer. The pale blue dot photo was taken from a distance that's nothing on cosmic scales. 3.7 billion miles sounds like a lot, but it's only about 40 times the distance from Earth to the Sunday. It's barely out of the solar system. From the nearest star, Earth would be completely invisible, lost in the glare of the Sunday from another galaxy. Our entire solar system would be invisible. And yet, that tiny pale blue dot is home to everything we know. Every thought, every emotion, every moment of joy and sorrow, all of it happened there. As humans, we evolved to understand things at human scales. We're good at judging distances of a few feet or miles. We can visualize objects from the size of a grain of sand up to mountains. But cosmic scales are beyond our intuitive grasp. When we talk about light years, billions of galaxies, and trillions of stars, these numbers lose meaning. They're too large. Our brains didn't evolve to comprehend such scales. We can do the math, we can write down the numbers, but we can't truly visualize what they mean. This is why analogies and scale models help. When we say the Sun is 1 million times larger than Earth by volume, that's a fact. But it's hard to grasp. When we say that if Earth were a marble, the Sun would be a sphere about 10 feet across, that's easier to visualize. But even these analogies break down at larger scales. When we try to compare Earth to the observable universe, the numbers become so extreme that no analogy works. There's simply no way to make it intuitive. The best we can do is accept that Earth is tiny. We can't fully grasp how tiny, but we can understand it intellectually. We can do the calculations, compare the numbers, and recognize that Earth's size compared to the universe is so small that it's almost zero. This realization can be humbling or even frightening. It can make us feel insignificant, but it can also be liberating. Because if Earth is so small, then our problems, viewed from a cosmic perspective, are also small. The things we worry about, the conflicts we engage in, the status we seek, all of it matters on Earth, but means nothing to the universe. This doesn't mean we should stop caring about things. Our lives matter to us, and they should. But a cosmic perspective can help us keep things in proportion. It can remind us that we're all on the same small world, sharing the same tiny speck of dust in a vast cosmos. So, where does all this leave us? We set out to discover how small Earth really is, and the answer is clear. Earth is incredibly, almost unimaginably small. Compared to the Sun, Earth is tiny. Compared to Jupiter, Earth is small. Within the Milky Way's 100,000 light-year expanse, Earth doesn't merely shrink, it ceases to register as anything measurable. Against Laniakea's 520 million light-year breadth, Earth transcends mere invisibility, it approaches conceptual non-existence. Measured against the cosmic web's filaments, Earth's dimensions fall below any meaningful threshold smaller than quantum uncertainty. If the observable universe were a vast ocean, Earth wouldn't be a grain of sand on a beach. It would be smaller than a single atom in that grain of sand. Actually, it would be far smaller than that. There's simply no adequate comparison. But Earth is also precious. As far as we know, it's the only place where life exists. The only place where consciousness has arisen. The only place where beings like us can look out at the cosmos and wonder about their place in it. Size isn't everything. What matters is what's here. And what's here is remarkable. Life in all its diversity. Consciousness capable of understanding the universe. Art, music, love, joy, all the things that make existence meaningful. Earth might be small, but it's our home. And in a universe that's mostly empty space, mostly cold and dark and hostile to life, a small, warm planet, teeming with life, is incredibly special. The universe is vast. Earth is tiny, but Earth is also home, and sometimes that's enough. It's worth reflecting on how we came to understand all this. For most of human history, we had no idea how small Earth really is. Ancient people believed Earth was the center of everything. The sky was a dome overhead with lights fixed to it. The sun, moon, and planets moved around us. We were special, central, important. This geocentric view made sense based on observation. When you stand on Earth and look up, it certainly appears that everything revolves around us. The sun rises in the east and sets in the west. The moon goes through its phases. The stars wheel overhead in predictable patterns. All of this seemed to support the idea that we were at the center. Greek philosophers like Aristotle developed elaborate models of the cosmos with Earth at the center. These models worked reasonably well for predicting planetary positions. They could explain the motion of the planets, though the explanations became increasingly complex. Planets didn't move in simple circles around Earth. They moved in circles that moved in circles, called epicycles. This geocentric model dominated Western thought for nearly 2,000 years. It wasn't just an astronomical model, it was deeply connected to philosophy and religion. Earth being at the center meant humans were central to creation. We were the point of everything. The cosmos existed for us. The first major challenge came from Nicolaus Copernicus in the 16th century. Copernicus proposed that the sun, not Earth, was at the center. Earth was just another planet orbiting the Sunday. This heliocentric model was simpler and more elegant than the geocentric model. It didn't require epicycles. Planets moved in relatively simple circles around the Sunday, but Copernicus's model was controversial. It challenged deeply held beliefs about humanity's place in the cosmos. If Earth wasn't at the center, were we less important? The Catholic Church initially opposed heliocentrism, seeing it as contradicting scripture. In the early 17th century, Galileo Galilei provided evidence for the heliocentric model. Using one of the first telescopes, Galileo observed the phases of Venus, showing that Venus must orbit the Sun, not Earth. He also discovered 4 moons orbiting Jupiter, proving that not everything orbited Earth. These observations were powerful evidence for heliocentrism. Galileo faced opposition from the Church. He was tried by the Inquisition in 1633 and forced to recant his support for heliocentrism. He spent the rest of his life under house arrest. But the evidence was clear. Other astronomers confirmed his observations. The heliocentric model gradually gained acceptance. Johannes Kepler refined the heliocentric model by showing that planets orbit in ellipses, not perfect circles. Isaac Newton explained why planets move the way they do through his law of universal gravitation. By the 18th century, heliocentrism was firmly established. Earth was no longer at the center of the cosmos. We orbited the Sun like the other planets, but people still thought the Sun might be at the center of the universe. After all, the Sun was special. It was the largest thing we knew. Surely it occupied a special position. In the early 20th century, astronomer Harlow Shapley studied globular clusters, dense collections of stars that orbit the Milky Way. By mapping their positions, Shapley determined the size and structure of the galaxy. He showed that the Sun was not at the center of the Milky Way. We were about 2/3 of the way out from the center, in a minor spiral arm. So we weren't at the center of the solar system, and we weren't at the center of the galaxy. Each discovery pushed us farther from the center, making us less special in cosmic terms. In the 1920s, Edwin Hubble made an even more profound discovery. He observed galaxies beyond the Milky Way and measured their distances. This showed that the Milky Way wasn't the entire universe. It was just one galaxy among many. Hubble also discovered that galaxies are moving away from us, and the farther away they are, the faster they're receding. This led to the Big Bang theory, the idea that the universe began in a hot, dense state and has been expanding ever since. These discoveries revolutionized our understanding of the cosmos. The universe was far larger than anyone had imagined. It was filled with billions of galaxies, each containing billions of stars. And Earth? Earth was one planet, orbiting one star in one galaxy among billions. We were no longer central. We were peripheral, ordinary, insignificant in cosmic terms. In the decades since, our understanding has continued to expand. We've discovered exoplanets, showing that planets are common around other stars. We've mapped the cosmic web, revealing structures on scales of billions of light years. We've measured the expansion rate of the universe and discovered dark matter and dark energy. Each discovery has reinforced the same message. The universe is vast and Earth is tiny, but these discoveries haven't made life meaningless. If anything, they've made it more precious. Because in all that vastness, Earth is the only place we know where life exists. We might be tiny, but we're also unique, at least as far as we know, given the enormous size of the universe and the vast number of stars and planets. A question naturally arises. If life is possible, shouldn't it be common? And if life is common, where are all the aliens? This question is known as the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" during a lunch conversation in 1950. The paradox is this: the universe is old and vast. Even if intelligent civilizations are rare, There should be many of them scattered across the galaxy. Some should be millions or billions of years older than us. They should have had time to colonize the galaxy. So why haven't we detected any sign of them? There are many proposed solutions to the Fermi paradox. One is that intelligent life is incredibly rare. Maybe the jump from simple life to complex life is extremely difficult. Maybe intelligence rarely develops. Maybe technological civilizations tend to destroy themselves shortly after developing advanced technology. If any of these are true, we might be the only intelligent species in the galaxy or even the universe. Another possibility is that civilizations exist but are staying quiet. Maybe they've learned that broadcasting your presence is dangerous. Maybe they're deliberately avoiding contact with other species. Maybe they're waiting for us to reach a certain level of development before revealing themselves. Or maybe civilizations exist, but communicate in ways we can't detect. We've been listening for radio signals, but maybe advanced civilizations use something else. Quantum communication or technologies we haven't imagined yet. Another sobering possibility is that space is simply too big. Even if civilizations are common, the distances between stars are so vast that contact is effectively impossible. A radio signal traveling at the speed of light would take years, decades, or centuries to reach even nearby stars. A reply would take just as long. A conversation with another civilization would be impossibly slow. And if you wanted to physically travel to another star, with our current technology, it would take thousands or tens of thousands of years. Even with hypothetical future technology, journeys between stars would take decades or centuries. The galaxy might be filled with civilizations that will never meet because the distances are too great to cross. This isolation is one consequence of Earth's smallness. We're tiny, and we're separated from other potentially habitable worlds by vast gulfs of empty space. Even if life exists elsewhere, we might never know. The universe's sheer scale might ensure we remain alone, practically if not literally. The smallness of Earth raises another profound question. How did life arise here? Was it inevitable, or was it a cosmic accident? Something incredibly unlikely that just happened to occur on our tiny planet? We don't know the answer. We have only one example of life, the life on Earth. Every living thing on our planet, from bacteria to blue whales, shares a common ancestor. All life on Earth is related. We all use the same genetic code, the same basic biochemistry. This suggests that life arose once on Earth, and everything living today descended from that original life form. But how did that original life form arise? We don't know. The origin of life is one of the biggest unsolved questions in science. We know that about 4 billion years ago, Earth had liquid water and a variety of chemical compounds. Somehow, in that environment, non-living chemicals organized themselves into something that could reproduce and evolve. But the details remain mysterious. Some scientists think life arises easily, wherever conditions are right. In this view, the universe might be teeming with life. Others think life requires an incredibly unlikely series of events. In this view, life might be extraordinarily rare, perhaps unique to Earth. We also don't know how common complex life is. Simple life, single-celled organisms, might be common, but complex life, multicellular organisms with specialized tissues and organs, might be much rarer. On Earth, simple life existed for about 3 billion years before complex life appeared. That's a long time. Maybe the jump from simple to complex is very difficult, and intelligent life might be rarer still. Intelligence, at least the kind humans have, might require a very specific set of conditions. It might be so rare that we're the only intelligent species in the galaxy, or even the universe. If that's true, then Earth's smallness takes on a different meaning. We might be tiny, but we might also be carrying something incredibly precious. Consciousness, intelligence, the ability to understand the universe. These might be extraordinarily rare in the cosmos. Earth, small as it is, might be the only place in billions of light years where the universe has become aware of itself. That's a staggering responsibility. It means that what happens on Earth matters, not to the universe, which doesn't care, but to the universe's ability to know itself. If we destroy ourselves, if we render Earth uninhabitable, we might be extinguishing the only light of consciousness in a vast, dark cosmos. Let's look ahead. What does the future hold for Earth? In the short term, the next few million years, Earth will remain largely as it is. The continents will continue drifting slowly. The climate will change, but Earth will remain habitable. Life will continue evolving. If humans survive, we'll continue to develop and change. In the longer term, about 1 billion years from now, the sun will start to heat up as it ages. The oceans will begin to evaporate. Earth's surface will become increasingly inhospitable. Complex life will struggle to survive. Eventually, Earth will become too hot for any life as we know it. In about 5 billion years, the sun will exhaust its hydrogen fuel and begin fusing helium. It will expand into a red giant, growing so large that it will likely engulf Mercury and Venus. Earth might survive on the outer edge of the sun's expanded atmosphere, but it will be a scorched, lifeless rock. Eventually, the sun will shed its outer layers and become a white dwarf. Earth, if it survives, will orbit a small, dim star that provides no warmth. The planet will be a frozen, dead world orbiting in permanent darkness. But that's billions of years away. For now, Earth is a vibrant, living world, the only world we know that's teeming with life. And there's another future to consider, the future of human exploration. If humans survive and continue to develop technology, we might one day leave Earth. We might establish colonies on Mars, on the moons of Jupiter and Saturn, perhaps even in orbit around other stars. If that happens, Earth will remain important as our birthplace. But it won't be our only home. We'll be a spacefaring civilization spread across multiple worlds. Earth will be one planet among many that humans inhabit. But even if we spread throughout the galaxy, even if we eventually inhabit thousands of worlds, the scale of the universe will remain humbling. The Milky Way is just one galaxy among trillions. Human civilization, no matter how far it spreads, will occupy only a tiny fraction of the cosmos. As we approach the end of our journey through the cosmos, it's worth pausing to consider what makes Earth truly special, despite its infinitesimal size. The universe operates on principles of physics and chemistry that are the same everywhere. Stars form, burn, and die according to universal laws. Planets coalesce from dust and gas through gravitational attraction. These processes happen throughout the cosmos in billions of galaxies, around trillions of stars. Yet Earth stands apart in one crucial way. It harbors something that might be extraordinarily rare, or even unique. The emergence of complexity from simplicity, the organization of matter into living systems, and most remarkably, the evolution of consciousness, capable of comprehending its own cosmic insignificance. Think about that paradox for a moment. We're standing on a planet so small, it essentially doesn't exist at cosmic scales, yet from this vanishing point, we've managed to measure and map the entire observable universe. This is perhaps the greatest mystery we face. How did unconscious matter organize itself into conscious observers? How did atoms, following blind physical laws, arrange themselves into beings capable of wonder, of asking questions about their own existence? The fact that you're listening to these words right now, understanding them, contemplating your place in the universe, is perhaps more remarkable than any of the vast structures we've discussed tonight. Earth might be tiny, but it has accomplished something that billions upon billions of other worlds apparently have not. It has produced a biosphere, an interconnected web of life spanning millions of species, each playing a role in maintaining the conditions that allow life to continue. It has produced intelligence capable of technology, of art, of science. It has produced beings who can look up at the night sky and, through nothing but thought and observation, determine that those points of light are actually distant suns, that our galaxy is one among trillions, that the universe is expanding and had a beginning. This brings us to a sobering realization about responsibility. If life is rare, if consciousness is even rarer, then what happens on Earth takes on cosmic significance. We are, quite possibly, the universe's only way of knowing itself. Through us, through our observations and our science, matter has become aware of matter. The universe has produced structures, us capable of understanding the universe. That's either a common occurrence, repeated countless times across the cosmos, or it's extraordinarily special. We don't know which. But until we find evidence of life elsewhere, we must act as though Earth's biosphere, and especially its intelligent life, is precious beyond measure. Every species that goes extinct on Earth isn't just a loss for our planet. It might be a loss for the entire universe. Every potential future where humans fail to survive and spread isn't just a tragedy for our species. It might mean the permanent silencing of the universe's ability to comprehend itself in this corner of space. This perspective should inform how we treat our planet and each other. The conflicts between nations, the competition for resources, the damage we do to Earth's ecosystems, all of this takes on a different character when we remember where we are. We're not fighting over a large territory. We're fighting over different parts of a dust speck. We're not competing for the resources of a vast world. We're competing for the resources of something almost too small to measure against cosmic scales. If other intelligences exist out there, looking back at us from distant worlds, what would they think of how we've chosen to use our brief moment of awareness? Would they understand our divisions and conflicts, or would they see them as incomprehensible given the preciousness of consciousness in a vast, mostly dead universe? Looking far ahead, beyond Earth's eventual demise, we can ask, what is humanity's ultimate potential? If we survive the next few centuries, if we learn to live sustainably on our small planet or spread to others, what might we become over millions or billions of years? The universe will remain largely hospitable to life for trillions of years. Stars will keep burning, planets will keep orbiting, the laws of physics that allow complexity to exist will remain in force. If humanity or its descendants survive and spread, we could potentially outlive not just our planet but our Sunday. We could witness the gradual evolution of our galaxy, see stars being born and dying, watch as the Milky Way and Andromeda merge into a new galactic structure. Our descendants might spread not just through our galaxy, but to others. They might develop technologies we cannot imagine, technologies that make interstellar travel practical or even routine. They might transform themselves, merging with machines, or adopting new forms better suited to space travel or life in extreme environments. They might seed the galaxy with new life, taking Earth's biosphere and replicating it on thousands or millions of other worlds. Or they might fail. Civilizations might be fragile things, brief sparks of consciousness that flicker and die on cosmic timescales. We might destroy ourselves through war, through environmental collapse, through technologies we develop faster than we develop the wisdom to use them. Earth might return to a world of simpler life, or even to a lifeless state, and the universe would continue on, vast and uncaring. The choice, to the extent we have one, is ours. Earth is tiny, yes. Our individual lives are brief, yes. But the cumulative effect of billions of humans making choices, developing technology, creating knowledge, and passing it to the next generation has brought us to a pivotal moment. We are the first species on Earth capable of comprehending the cosmos. We're also the first capable of either spreading life beyond our planet or extinguishing it entirely. We've covered a lot of ground tonight. We started with Earth and zoomed out, comparing it to larger and larger structures until we reached the observable universe itself. And along the way, we discovered something profound. Earth is small. Smaller than most people realize. When you compare it to stars, galaxies, and cosmic structures, Earth becomes so tiny that it almost disappears from view. If you made a scale model of the observable universe, Earth would be far smaller than an atom. It would be smaller than anything you could possibly see or measure. It would be, for all practical purposes, non-existent. But Earth is also home. Every human who's ever lived has lived here. Every thought, every emotion, every achievement, all of it happened on this small planet. Earth might be tiny in the cosmic sense, but it's everything to us. And here's the remarkable part. We can understand this. We can comprehend, at least intellectually, how small we are. We can look out at the universe and grasp its scale. That's extraordinary. That's what makes us special. Out of all the planets in all the galaxies, Earth is the one that produced beings capable of understanding the universe. We might not be alone in this. There might be countless other civilizations out there looking up at their own skies and wondering about the cosmos. But we don't know that for certain. Right now, Earth is the only place we know where conscious life exists. That makes Earth precious beyond measure. Size doesn't determine value. What matters is what's here. And what's here, on this tiny planet, is something remarkable. Life, consciousness, the ability to wonder, to question, to seek understanding. So yes, Earth is small, but it's also irreplaceable. It's the only home we've ever known. And in a universe that's vast and mostly empty, a small world full of life is something to treasure. The next time you look up at the night sky, remember what you've learned. The stars you see are part of the Milky Way, our home galaxy. Those stars are suns, many with their own planets. And our galaxy is just one of trillions scattered across an almost unimaginably vast cosmos. Earth is tiny in all that vastness. But Earth is also home, and that matters more than size ever could. Thank you for joining me on this journey across the cosmos. If you found this exploration meaningful, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep explorations of space and our place in it. And remember, you're standing on a planet that's tiny beyond comprehension when compared to the universe. But you're also standing on the only world we know that's home to life, consciousness, and wonder. That's something to celebrate. Sleep well tonight, knowing that you're part of something vast and beautiful. The universe is enormous. Earth is tiny, but Earth is precious. And you, living on this small world, are part of its story. Good night.